this Hambian KVL, KCL, and equivalent resistances, right? So the first thing
Mm.
is KVL. What KVL means is the sum of the voltages in a loop add up to zero, right? So battery, resistor, simple, right? So you have a 5 volt battery and you have a resistor R, yeah, and we'll have a current, obviously. So I don't know if you remember when I show you this simple form when I had the resistor and the current flowing through it, I.
Mm-hmm.
So we have plus to minus. There's always the configuration of the resistor. Always remember this diagram here. Always keep it in the back of your mind, right? Okay, that's help you to do majority of the questions. So anyway, so in this case you have voltage. So obviously in this direction you're seeing a voltage drop, right?
Yeah.
Okay, going from plus to minus. And if the current moves in the opposite direction, it will be a voltage rise. See, you know?
Yeah.
That's basically what you're using. And it makes sense because, well, in this case, remember, voltage is like water. Remember, I showed you that? So it's like water. If you and the resistor is like a real thirsty person, yeah. Every time you pass a thirsty person, you're gonna be gaining more water. You're gonna be losing water.
Losing.
Correct. So the voltage had to match that. So it had to be negative, right? And the polarity of the most of the time the polarity will tell you, right? But if they give you the polarity, you have to use it, right? If they don't give you the polarity, like a random resistor, you have to assume the voltage drop polarity. So I didn't do loop analysis with it, but remember when you do in loop, they don't really give you the polarities of the resistors. They don't just give you the resistor. I don't know if you remember that. So when they just give you the resistor, you had to assume the voltage drop across the resistor to be positive or negative. Yeah, I didn't do loop with as yet, but I basically do. But say I have case one is when they actually give you the polarity. So if they give you the polarity, you know if it will be positive or negative, right?
Mm-hmm.
And then if they don't give you the polarity, you had to assume the polarity. That makes sense, right? Because I
Yeah.
mean, it's kind of trivial. If they give it, use it. If they don't, you need it, so you assume it. Yeah, they're kind of similar to when you're doing nodal. When I say assume the direction, the current direction into the node and out of the node, it's kind of the same thing. That's for loop. Cause this is a loop, right? So, but anyway, so I'm gonna assume if you use KVL, right? The sum of the voltages in the loop had add up to zero. So you just pick an arbitrary starting point, and then, well, obviously you're going around the circuit, right? And you're adding up the voltage. So, so do the sum, right? So from minus to plus will be plus 5 or minus 5.
From.
Right here, so it'll be 5. And then we'll reach here, and we go here. Then this resistor here, yeah? So
Mm-hmm.
normally the consensus is let me just write it down, right? This here is normally the consensus. So current going through a resistor, the voltage drop will be negative, right? Yeah?
Mm-hmm.
This,
Yeah.
because this here is basically this pattern. This have to be plus, and this have to be minus, right? It just have to be because normally the current will flow from a high to a low potential, right? So you know for sure it's like this. It can't be anywhere else, right? That's why I said memorize this form, okay?
Yeah.
Anytime the current flowing through a resistor, the plus side is on this side and the minus side is on this side, right? So in this case here, if we're going from plus to minus, the voltage will be positive or negative.
Negative.
Yeah, well, that makes sense. Because you had to get zero somehow. It can be, if it's plus, it could be plus, in this case, IR, right? How you
Mm-hmm.
gonna get zero from that? It's gonna be bigger number, right? So it had to
Yeah.
be minus for you to get zero, right? So, and basically this is it. This here is basically this. You're seeing it, right? So
Mm-hmm.
obviously you see the arrow plus to minus will be minus, right? Cool. And even if it was to go in the opposite direction, so let me say I'd start here instead. So you'll go from plus to minus, which is a minus 5, right? See, you know? If you go
Yeah.
this way. And when you reach here now, when you go in this way, you notice that the polarity just swap. Notice that? You're still keeping the plus and the minus, right? Because always remember, this had to do with conventional flow, right? Okay? This conventional flow. Conventional flow is in this direction, okay? So if you reverse it, the plus and the minus will still stay there, right? Yeah? So it'll still be plus and minus is a minus. And then from here now, a minus, that plus will be a plus, right? And well, obviously this will give you 0. And I basically what KVL is, all KVL is the first thing you do is you look for the polarities across the components. Because the polarities will kind of tell you the voltage drop, right? Then you just go around the loop and you sum the voltages. And that is it. That really sure it is. The hardest thing, or the thing that will trick you up, is the resistor. And all you have to remember is current in this direction plus to minus, voltage drop, voltage rise. And that's literally all you have to remember. And it's conventional flow. Alright? Alright, so any questions on that?
No.
Cool. Alright, so the next one is KCL. And that is Kirchhoff's current law, right? This is the easiest thing on the face of the earth. Alright? All this is the sum of the currents entering a junction is the same as the sum of currents leaving, right? That's literally what it is. So this is our junction, right? That makes sense. You drew before, right?
Yeah.
Or it like was in a car before and you have what came from
Yeah.
a junction, right? So it's a junction. It's
Mm-hmm.
the same thing on a circuit. Okay? So all you're looking for is in KCL is the arrow directions, right? So this arrow going here, 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 right? So this is the junction here. Okay? So if this is 1, this is 2, and this is 3. So asking you some questions here, right? So
Mm-hmm.
entering. Which numbers they enter in the junction?
1 and 2.
Hmm. And which one's leaving?
Mm.
Correct. So therefore, by the law, 1 plus 2 is equal to 3, right? Yeah? Let me see what this. That's
Mm-hmm.
all KCL is. Let me try one more, and then I recap it for. Alright. Mm, I was mixed up in name. It's
Well,
Maya. It's Maya, right? Damn
yeah.
it. I was telling myself Ma. Anytime I see the M and E, I'm thinking Ma. Anyway, Maya. I remember it. I'll just change the name from on the phone to MI. So when I see the name, I could be like, why? That's just for me, right? That's
Okay.
not for you. Then you go and see the name and rename it. Right. Whew. And bracket, I'll put MA. Right. Okay. Where's what? At least I get it correct this time. Anyway, so we started already. I recorded it. So, yeah, that's right. Watch the first piece if you need to. But I'll just continue, right?
Yeah, no problem.
Yeah. But we just do KVL and KCL, right? So I'll just go through it one more time. Yes.
Okay.
All KCL is, you see, there's a junction, right? You'll see this all over the question, all the time. So the sum of the currents entering is always the sum of the currents leaving, right? So if this is A, this is B, and this is C, right? This here is the junction, okay? And it's good to just draw a dot on it to make it a little bigger, right? So Maya, which numbers they enter in the um junction?
A and B entering, C leaving.
Correct. So therefore, by the law, the sum of the currents entering is equal to the sum of the currents leaving, right? So if this was, so that's how the question will come. They'll get a set of this, and they'll say this is 3, they might say this is 10 amps, right? And they'll say find um, I1, right? All they do is basically, right, which one enter? Anybody, which currents they enter. So now you have values, right? So you just use what it. So here's obviously 3 plus I1, right? Everybody agree with that? 3 and
Yeah.
I1 entering, right? And
Yeah.
10 amp leaving. You have an equation you could solve. So I1 will equal to 10 minus 3. So I1 is equal to 7, right? Everybody understand what I did there?
Yeah.
So
Yeah.
7 plus 3 is 10, right? That's literally what it is. You're just looking at the arrow direction. So you're looking at the arrow directions. That's really all it is. Obviously, by law, you can't have this. Anybody can tell me why you can't have this? Well, you could, but you can't. Think about it. Anybody can tell me why that can't. Alright, so which currents they entering? Anybody can tell me the currents entering?
All.
Alright, cool. And which currents leaving?
None.
But okay, I'm gonna put it in a practical here. If you have somebody to make a house fair, right? And you know them doors that could only open one way, I'm
Yeah.
waiting for everybody to say yes. On my, you know about
Yeah.
that door? Okay.
Yeah.
What if he make the house and all the doors he make could only open in one direction? What gonna happen to you? If you're inside and the door could only open from the outside, how you gonna get outside? You can't get outside, right? So with currents, you need somewhere to leave. You can't just come in and just be there. It need flow. Any current flow in there, there's no flow there. There's no exit. Yeah. So you need to have at least one exit, right? But you will never see this in a circuit. You need to have at least one way of getting outside. Like one door had to open from the inside to go outside. At least one. Everything else could be entered, but you had to have a way to leave. Right? So everybody cool with that?
Yeah.
Yeah.
Cool. So that KCL, and that KVL, Maya, all KVL is the sum of the voltage in the loop. So we did loop analysis, right, Maya? So this is kind of basically what I was using. So any loop, this is a simple loop, right? Sometimes it will give you the polarity across the resistor, right, Maya? And remember this little diagram I'll show you with the current and the resistor and the polarity.
Yeah.
So when you're in the direction of the current, there's plus to minus across the resistor, right? So that's a voltage drop. Remember that? And obviously in the opposite direction, against the direction of the current, is a voltage rise. That makes sense?
Yeah.
And so that is when they give you the polarity. So in the question, when you look at the tutorial, sometimes they will give you the polarity across the components. If they give you the polarity, you have to use it, right? And then sometimes they won't give you the polarity, like when you're doing loop analysis. So when they didn't give you the polarity, remember we say we assume the voltage drop across the resistor to be positive or whatever. Like basically do it.
Yeah.
So if they give you the polarity, use it. If they don't, assume it. But when you assume it, yeah, they use it everywhere. You can't be swapping and thing. Yeah. Okay, that is two. Three. Last thing. Key. This is the easiest thing on the face of the earth, right? Or at least how I show it. If you could remember this, you're gonna be a boss. You can bring any math circuit for you. This gonna be chalk and cheese, right? So I'm gonna show you that if at any point any of you are confused, please stop me, okay? I want you to stop me, right? I don't wanna explain it over, okay? Because once you get it, it's like basically that's it. So let me see how this draw a math circuit. Alright, cool. So everybody seeing this circuit, right? Any
Yeah.
Yeah.
question, they will say they will kind of like remove one and they will say this is A and this is B and they'll say R here and they'll put the arrow like this, right? Looking familiar? So when you do this, what you do, step one, is kind of nodal analysis by using nodal analysis to get the resistance, right? So step one, you're drawing your nodes. That should be easier and everybody should know what a node is. So this is node A because obviously that would give you any outside, right? And this is node B. This whole thing here is node B, right? You shouldn't have any issues drawing any nodes, right? Because remember it's bounded by the components, right? So once you start to draw, just draw, okay? And we'll have our next node on, so you can label this, well, this is B, because that way here, right? So I'll let you in just now. And then the last node is up here. Well, not really last, but we could say this C. We have, I think I draw C wrong. C was bigger. We see, so that'll be here. It will come through here, come around here, come around here. And this is C, right? All this is C. And this is D. Right. Everybody okay with what I did there, right? Drawing any nodes? Everybody could I the first piece?
Yeah.
Everybody could. Kind
Yeah.
of look weird, but remember node just bounded between the components, right? So that's step one. Alright, step two. You draw a line diagram of the nodes. So it kind of look like this. So what you need is the start node, the between, and the end, right? So it looks something like this. I might have to zoom out. Oh, let me add lettuce money. Right. Kazari. Mr. Vincent. Right there, man. So, well, I'll wait for him to hear.
Yeah, we are now.
Alright, yeah, cool. So, you all had a tutorial. I think they gave you all a tutorial, right? So, just going through the tutorial, um, you can do the questions, send it to me, I'll correct it, and we'll go from there. So, I'll record in the session, so you could always watch the beginning, right? So, but I mean, when I start the question, I'll be going through the content again. So, you can again, I double down. Okay? So, anyway. So for now, that's following. So the equivalent circuits. So guys, why you're doing this is that when you get a math circuit, but like it looking like a real weird. Like you can look at that and be like, yeah, that in series, or yeah, that in parallel. Like you will not know. Yeah, I can't tell. Right? Like that looking weird. So the first thing you do, Vincent, is you draw in your notes. So if you look at the tutorial or the assignment, however, the last few questions asking you for equivalent resistances, this is what you would do, right? So the first thing you do, you draw in your nodes. So you kind of use a nodal analysis to do it, but not really nodal analysis. You just use a nodes to get the resistance. So step one, you draw in your nodes. So that's what we did here. So this is A, B, C, and D, right? The second thing, you have to draw a line diagram. So you start with the starting node, the in-between nodes, and the end node, right? So the start node obviously is here, right? Because the arrow for the resistance going through here. So it will go through here and it will come out here. So you're starting at A and you're ending at B obviously. And you're just drawing the in-between nodes. So we have C. You try to keep it sequential, right? So don't put D here, because that wouldn't make sense. Because in the order in which the nodes come in, A here, then is C, and then is D, and then B last, right? So these are the nodes that you have. So you have a A node, your C node, your D node, which I draw a little big, and you have your B node, right? Remember, you want the resistance across these two. So everybody good with what I did here? Speak now for a whole piece. Let me know. So you're drawing your nodes. After you
Yeah.
drain all your nodes, you have your starter node, your end node, and the nodes in between. So this is your start node. So you draw it first, obviously. And your end node, you draw it last, right? This is the end. And these are the in between, right? So it is between. If you look at your diagram, it's A, then C, then D, and then you have B there, right? So that's that. That's really all it is. And this is where the fun does start. So let's go and erase these. It's really easy. It's just chalk and cheese. So you're taking a pencil, and this way you do it. This here, oh God, I didn't give out values. Let me just say all the resistance is 2, yes? To keep it simple. I think that is all. 2. All of them is 2. Obviously, any question will be different, right? But it's the concept you're looking for. So this resistor here, the question you're asking yourself is what nodes it between? And you just put it between what it between. So this 2. So Maya, yeah, no? So this first
Yeah.
resistor here, what two nodes it in between?
A and C.
Right, so you draw between A and C. So from A, you connect it to C. That makes sense? And when you do that, you cross it out, right? So you do it already. So when you're doing this, every time you handle a resistor, make sure and cross it out, right? Because you run the resistor like doubling it again now. Because you're gonna forget where you put in the diagram. Alright, it's Babulal. I think it's Babulal. Oh, did I pronounce it correct? I'll call it V. So V, there's 2 ohm resistor here, right? Which two nodes it in between?
A and B.
Correct? Well, it is draw between A and B. So this is A here, and this is B here, right? See now?
Yeah.
So you had to go from here straight across. Obviously, there is a sign between, right? Straight across the B. That makes sense?
Yeah.
Cool. So like that. Cross out. We go in. 2 ohm here. So I'm zoom. So Mr. Vincent. Yeah, no? So there's 2 ohm here, right? Which two nodes it in between? I'm gonna zoom in so you can see. What
C
two nodes
and
that 2 ohm resistor in between?
C and D.
Where's that?
C and
Yeah,
D.
yeah, C and B. So talk a little louder, right? 'Cause it's kind of soft on mine. Alright, so C
Oh,
and B.
yeah.
So C and B. So obviously C here and B on that side here, right? Everybody seeing that, right? And they cross out. So we have more resistors. Maya, your turn again. This resistor here. I don't know if you see the
C
diagram
and
yet.
D.
What is that?
C and D.
Correct? It says C and D. So it'll be here and D, right? And here, cross outs. Alright. Babulal. This resistor here. What two nodes it in between?
B and B.
Correct? We just draw between B and D. So like two. Cross out. Alright, Mr. Vincent. So there's two of them here. Let me zoom in. So you can see. So this one here. What two nodes it in between?
C and B.
So the same thing as before, right?
Yeah.
Okay. So anytime you see something between the same node, it in parallel, right? That kind of trivial, right? So this in parallel. So like two of them here. So how much more we have? We did this one. Have any more? Right, well. Maya, finish it off first. There's two of them here. What two nodes is in between?
D and B.
Correct is right. So therefore, our next parallel, right? Let's draw that in there. Pow.
D and B. Nah.
Oh,
You
oh,
do
all
C
right,
and
right, 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 right.
D.
Thank you very much. Thank you. So between E and B. Thanks. Alright, cool. Well, let's erase this thing here. Alright, so basically we kind of done. But what this has allowed you to do, it's way easier to see what in parallel and what in series. I don't know if you realize. Like, you could clearly see the things that in parallel, and you could clearly see how this whole circuit go and boil down like Baji. So my first question to all three of you, and how everybody to answer it, everybody's seeing that between C and D, those two resistors, they're in parallel.
Yeah.
Yeah.
Everybody's seeing that, right? Okay, cool. Second question for everybody, or everybody to say yes, no, or confused. Say it, right? Because that's how you will learn, right? I'm here to facilitate you. The two resistors between D and B. Everybody's seeing how they're in parallel, right?
Yeah.
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 Correct. Cool. Next question. The resistor between A and C and A and B. Everybody agree that that's in parallel?
You can repeat.
So A and C, the resistor between A and C, and the resistor between A and B. Everybody could agree that they're in parallel. So it look a little confusing. It's like how I saying it, yet it's implying that way you
Yeah.
have to say yes, right? But no. In order for something to be parallel, it had to be starting and ending at the same node, right? That makes sense?
Yeah.
Yeah.
Somebody leave or somebody now join. Oh, well. All right. Yeah, Vishal.
Yeah.
All right, cool. I'll continue. Right here. So fair enough. Last question. Everybody remember how to do parallel, right? So remember for parallel, well, there's more for Vincent, right? Is product over sum, right? Everybody remember this? So that is how you do
Yeah.
it quick. And well, for Vincent, this is for two resistors only, right? So if you have like four, you gotta do them two at a time and then break it down, right? So what I mean by this, Vincent, is that you say we have these two, this parallel combination here, right? If obviously we could combine it to one. So okay, then parallel. So this would be product of the two, which would be four over the sum, which is four. So this will boil down to one resistor. That is 1 ohm, right? And same thing for,
And
yeah,
what about the push straight?
if it's three, I have to do two. And that two, when it boils down to one, you do the one and the one after. Yeah? So you
So
could
yeah,
only
with
do it
the
3 at a
one
time.
how.
Where's that?
Okay, just repeat how it did with the one that's outside.
Well, oh, it's okay. So for it to be parallel, how it doesn't know our resistor parallel at the start and at the same node, right? So the resistor between A and C is not parallel to A and B because C and B is not the same node, right? That's why it's
Yeah.
not in parallel. That's all it is.
Okay.
Yeah. So look at C and D. You see in the two resistors between them, you notice how they start and end at the same node. Notice that? Same node these two here, B and D. Yeah.
Yeah.
So that's how you know they're parallel. I mean,
Okay.
kind of trivial. I think most of y'all could look and see that, hey, these two things is in parallel, right? But it's, yeah, so now about the three thing. So what you would do is you would do two at a time. So you do these two, and you do your product over sum, and you'll get one resistor, right? And then this will boil down to just this. See now? So this will give you one resistor now, which is this here. And you just combine it back with this, and you just go again. So you could only use this with two resistors at a time, right? You got do that, right? So that's something important to do. Well, sorry, to know. Okay, but we ain't finished yet. So what I do now, guys, is the trick is you start inside and you work outside. Well, work to outside. So obviously, well, you all could obviously do this for homework, right? Because this will take time to do. So this here will give you a 1 ohm resistor, right? This here will give you a 1 ohm resistor, right? You know what? Let me do it. Because I've been, right? I'll do it because I don't want to be too confused. Yes, it is. I want to take a picture from my phone because once I scroll, like problems. So let me give me a second to take a picture. Alright, cool. So now I can scroll down. So the first piece, yeah, E. So you had this here, and then from C to D, it will reduce to one resistor, right? Because two of them in parallel. A 2 ohm in parallel with a 2 ohm will give you a 1 ohm, right? Everybody agree with that, right? Because product over sum 4 and 4 is 1. And then same thing for the D and the B. It will give you a 1 ohm resistor, right? And then we could keep reducing. So between C and B, you had a next combination, right? Then this is a 2 ohm. So now, well, and then you have this big one going on top. So let's keep going. So we're working from the inside out. So obviously these two in series, yeah, that'll boil down to one resistor. That'll be two. 1 plus 1 is 2. Right? And just keep going. It's just work on the inside. So these two in parallel again. So you can reduce it to 1. So a 2 in parallel with a 2 is obviously, well, that's 1. This is 1. So once you start to simplify, you don't really care about the nodes anymore because you can kind of see the pattern once you start. Because at that point, it's just a circuit, right? So this is 2, 1, and what this was 2. And let's keep going. Let's keep going. Series. So these two in series. So this will be 3 and 2. And let's keep going. They're in parallel again. So product over sum. So that'll be 6 over 5. 2 by 3 is 6 divided by the sum. So you get 1.2. And that is the answer. 1.2. So this is A. Remember this was A. Remember this was B, right? The, the question was to reduce the resistances between A and B to 1. And that's what you did. So I'm going to run it through again. So we started with this big circuit here. Once you get this, The next time you draw it, just remove the A, B, C, and D because you don't need that anymore. The reason why I did that is so you could see what resistors in parallel and series and once you get that done, the next time you draw the circuit, just remove it. You don't need it anymore. Yeah, because you're trying to connect the circuit. So you start from the inside. Parallel, parallel, reduce. Yeah, on the inside you could get real parallels because it's on the inside, right? So one ohm here, one ohm here. That's only two parallel circuits, right? Obviously, if I was to redraw this, you notice how the circuit connected at no circle no more. So obviously these two here in series, right? So I add it up together and I get that. And obviously you're seeing these two in parallel. So I do that. And I get this here. Then you're seeing these two in series. So you do that. And it's in parallel with the big one. Product over sum. Okay, yeah. So and that's it. That's really all it is. So that's to recap these steps. When you say get the equivalent circuit, you draw any nodes. After you draw your nodes, you draw a straight line diagram. So you just need the start node, the end node, and the in between. You try to keep it as sequential as possible. So don't go and put A and then D after, because that really makes sense. Because technically C right after it, and then D and then B. And after that, you just draw in the resistors in between the nodes that it's supposed to be. And after you do that, you just reduce. Because it's a parallel and series. And that is it. Right? Anybody have any questions? Anything, any little thing. It don't matter what it is. Anybody have any questions?
Um, is equivalent circuits the same as source transformation?
Source, was that? Was it?
Yesterday he did source transformation now, so I'm not sure. I remember he was also summarizing the circuits like how he did it here. So I'm
Oh, it's
asking if
probably the
it's the
same thing.
same thing.
Well, I never learned it as source. I just learned it as equivalent circuit reduction. But if there is a name for it, well,
No, source transformation is when you go from a voltage source
mm,
and a resistor to a current source and a resistor.
oh, that is Tevin and Norton. That is what that is. Yeah, that is the equivalent circuit for the Tevin and the equivalent for Norton. Yeah, that is a transformation as well. But yes, this resistor thing you're doing here is part of the steps in order to get something called the Tevin equivalent circuit or the Norton equivalent circuit. This is one of the processes, right? So as Maya said, yes, you're reducing the circuit into, if it's Thevenin, you're reducing it into a voltage and a equivalent resistance, right? And if it's Norton, you're reducing it into a current source and a resistor. To get the resistor part, this is what you had to do. Okay? So I hope that, Maya, that was good, right? I hope that's what I was saying, right? That's what I was saying. Cool. Alright. Alright, anybody have any questions on it? So that is equivalent circuits. KCL, but all it really is just the sum of the currents entering the node. Not node, well you can say node, but really a junction, right? So the sum of the currents entering the junction are equal to the sum of the currents leaving, right? That is really all the laws. Any question, I will say a set of these junctions. Just look at the arrows. Once you see the arrows, you will know if entering or leaving, and you will know what the value is, because it had to add up to basically zero. But both sides had to be equal, right? Now, well, KVL, the sum of the voltages in the loop had to add up to zero. Remember this. Current in the going through a resistor, the voltage drop is negative. Yeah? Obviously, in the opposite direction is positive. So in this simple example here, if you're going like this, from minus to plus is 5, right? And then you're going through the resistor, so this will be plus to minus, right? And plus to minus is negative, so it'll be minus IR. Because it can't be plus, because you can't get 0 if you add it. Yeah, so that's really all it is. Like KCL, sum of the voltages in the loop added up to 0 in the correct polarity. KCL, the sum of the currents entering and leaving a junction, are they be the same, and equivalent resistance during the nodes